We are Team Inspectobot, and these are the members of our team.
Roshni Kaushik,
润江
Zhang Sang,
Amelia Bian. We're a 2016-2017 senior design team sponsored by Chevron. Our faculty sponsors are Dr. Gobel, Dr. Elliott, and Dr. Dabney.
$2.2 billion. That's how much was spent in 2014 alone on oil and gas pipeline inspection. Despite that much being spent, 3,300 incidents of pipeline leaks were reported in the past 5 years. So there's obviously a problem to be fixed here. The current solution for this problem are pigs, which are devices sent through pipelines to clean and inspect for cracks and defects. Pigs are very expensive, and the major problem with them is that they cannot negotiate complex pipe geometries, like changes in diameter or turns. With the motivation for our project being the large amount of money spent on pipeline inspection and the fact that some pipes just simply can't be pigged, the current project scope is to build a robot that can recognize different geometries in pipes and navigate those geometries successfully.
Previous iteration of Pipebot project achieved many successes, including classifying more than 90% of topologies correctly, achieving a sophisticated mechanical structure that allows the robot to move and fit in variable diameter of 5 to 7 inch. They also achieved a minimum speed of 2 centimeters per second, but there are areas for improvement as well. They classify the junction too late so that when the robot is already in the junction, they reach a result, and this is too late for the robot to turn. Also, they didn't conduct any test on turning success rate. Finally, the algorithm for classification is not very robust, so any slight changes in testing conditions will result in incorrect classification. We have 5 design specifications for this year's Pipebot. First is the minimum horizontal forward speed. The robot needs to move in a straight pipe at least 2 centimeters per second. And then for classification success rate, the Pipebot needs to correctly classify pipeline junction 90% of the time. Also, there's a distance requirement before entering the junction of classification. The robot needs to classify junction at least 2 centimeters before entering it. For neck turning success rate, the neck needs to turn to correct commanded angle 80% of the time. Finally, for variable diameter range, the robot needs to fit in 5 to 7 inch diameter pipelines.
Our robot is mainly composed of 3 parts: the head, the neck, and 2 body segments. The head part has a LiDAR sensor on it to collect the data of angle and distance from the pipe wall to the LiDAR sensor. And this information is sent to a BeagleBone, which is like a microprocessor on the neck. The neck also has 2 servos and a W joint, which add more flexibility to the neck when it turns. We also have 2 body segments that propel the robot to move forward. Each has 4 motors, 4 wheels, and 4 extension springs. One of our objectives is to have the robot move forward in a straight pipe at minimum 2 centimeters per second. And here's a video of the robot moving through a straight pipe at 6 centimeters per second.
This control flow shows the software side of the design. Based on the LiDAR sensor input, the classification detects whether there is a joint ahead. If there is no joint detected, the system would only command the motor and make the robot continue straight. If there is a joint detected, the classification part would give the distance to junction as an input to the motion planning and start the turning procedure. This is a picture of a scan result for a YRF junction. Classification is conducted based on segment analysis.
Here we have 2 videos of the robot executing 2 different turns. The first one is a UR turn. Basically, it's a U-turn to the right. The second one is a TR turn, which is the T-turn to the right.
The Pipebot project for the 2016-2017 year was a success. We significantly improved the classification success rate and implemented a successful neck turning mechanism. There are still avenues to be explored in this project, including waterproofing the robot and improving the integration of motion planning and classification. However, our project has successfully met all stated specifications and moved the project closer to a fully functioning, autonomous pipe inspection robot.
We are Team Inspectobot, and thank you for watching.